The authors of this presentation have no financial interest to declare. The existing literature on refractive surgery have many lacunae and unanswered questions which need to be answered. As a child, all of us have read the story of the 6 blind men and the elephant. Today we ophthalmologists are in the same situation, wherein while looking at any case, we interpret each machine and its parameter individually. Unfortunately, this keeps us far away from the whole picture. Let me take you through the journey of mathematics and how it helps us to explore the whole picture. In vivo measurement of biomechanics is very challenging and often limited options are available for the same. However, with the help of mathematical modeling, the true biomechanical property of the tissue can be measured. Finite element modeling is a type of mathematical modeling which has various applications ranging from aeronautics to medical sciences. Different types of finite element modeling that we are aware of include the forward FEM. In this method, by assuming the Young's modulus, the strain on the corneal tissue can be calculated. In inverse finite element modeling, the Young's modulus is calculated by taking the intraocular pressure and strain data from the corpus. Using this novel mathematical model, in our practice of refractive surgery, we take data from the pentacam, which is then run through a software to create a meshed model of the cornea. On addition of deformation data from the corpus, we can simulate the intraocular pressure and measure the corneal apex displacement. We applied this model to our clinics and compared the two most in-trend refractive surgeries, that is SMILE and LASIK. Comparing the results of post-operative 6-month data, we saw that SMILE was biomechanically stronger than LASIK. The next use of finite element modeling is predictive modeling. This unique model helps us to determine the biomechanical changes post-operatively and in turn predict the corneal tissue weakening. In future, we aim to use this novel mathematical model to predict keratoconus progression, to plan cataract incisions, and also to build new IOL formulas to correct surgically induced astigmatism. The next model is analytical biomechanical method. It is based on corneal waveforms and has the ability to separate out the corneal biomechanics from the extraocular biomechanics. On ethics approval, we performed yet another experiment in which we compared the total amount of weakening caused by only flap or cap after LASIK and SMILE respectively. We created only a flap or cap and remeasured the biomechanics after 4 hours of femtosecond cuts, after which the surgery was then completed. We saw that there was higher biomechanical weakening in flap as compared to the cap, proving that SMILE is biomechanically stronger procedure. Another emerging application of mathematics in the world of ophthalmology is Bowman's topography. We have constantly been in hunt for a perfect topographer. Studies have been published wherein they have done topography of patients after de-epithelialization. However, this is an invasive procedure. To fulfill the need of a non-invasive approach, we have incorporated mathematics with a high-resolution OCT and a topographer. We can now easily demarcate the air epithelium and the Bowman's interface using mathematics. Combining the tangential and axial curvatural data with ray tracing and Zernicke analysis, we can calculate aberrations and also derive topography of the underlying stroma without de-epithelialization. Looking at the future, artificial intelligence is no more limited to the outside world. It is on the verge of transforming our clinical practice. Taking inspiration from the Google DeepMind project, we intend to combine mathematics with patient demographics and clinical picture for better prediction outcomes. It is our dream to combine all the mathematical models and build a big prediction project. As a kid, I used to hate mathematics, so I became a doctor. But looking at its applications today, I am loving it.